So when we look at the derivatives of the form ax plus b, so whenever you have that form inside of another function, a chain rule happens. If we recognize what happens with the chain rule, it's going to help us work backwards and think, if we have an ax plus b inside of another function and we're integrating, what are we going to have to do to compensate for that chain rule? Most of you have done the first one already. Here's a check. What we've done first on the left side is the actual question. Then we say, let's replace the inside with ax plus b and see what happens. Second one with the natural log. You have a chain rule again. You do 1 over what's on the inside and then multiply by the derivative of the inside. So if we had natural log of ax plus b, we'd do 1 over that. Chain rule says keep that inside the same and then multiply by the derivative of the inside. And finally, we have an e to the x1, same thing. The derivative is itself, but then the chain rule says we have to multiply by 10. So if you had e to the ax plus b, the derivative is itself, and you'd have to multiply by a. So when the chain rule is of this form, in other words, the function inside is just a linear function, where the derivative is just a constant, we say to ourselves, well, if we were integrating and working backwards, we'd have to compensate for this a that we're multiplying outside. And the opposite of multiplying by a is dividing by a. Same thing happens with sine and cos. You know what the derivative is. When we do that chain rule, you'd multiply by a. You know the derivative of cos is negative sine. So when you take the derivative there, again, you have that chain rule where you multiply by a. So now we can generalize about what's going to happen when we do the integral of this. Well, if I have my normal power rule, I know that I'm going to have to add 1 to the exponent and divide by that exponent. That's what our power rule law has been so far. But now I'm going to also have to divide by a, because our chain rule always had that a multiplied at the end. So to get rid of that, we're going to have to divide by that a. So a couple of examples of how we could do this. If I wanted to find the indefinite integral, so the integral of 5x minus 4, I'm going to change that cube root to the power of 1/3. So here I'm finding the indefinite integral of 5x minus 4 to the 1/3. I would do my chain rule. My chain rule says add 1 to the exponent. So I'd have a 4/3 up there. I mean my power rule. And because it's a power rule, I would have to divide by that 4/3 as well. Now that the inside of my function is in the form ax plus b, if we were doing the derivative, when we do the derivative, at the end we'd have to do our chain rule, and the chain rule would say multiply by 5. So in order to compensate for that, when we integrate, we're going to also have to divide by 5. And then we have to remember plus c. Simplifying this, because the fraction on the bottom would be 20 over 3, multiplying by the reciprocal would give you 3/20, and then we write plus c still at the end. Here's another one for you to try. Again, noticing that you can change this into a power rule form is the key starting point. Add 1 to the exponent, divide by that, also divide by the 9 plus c. So if we can recognize a power rule, and we recognize a simple chain rule inside, and by simple chain rule, it's just ax plus b inside so that the derivative is a constant, then we can use our same rules we did for integrating before, and we're just adding the fact that we're dividing by that constant that's going to come out from the chain rule. So the same thing is going to happen whether we're integrating with natural log or e to the x, and later we're going to see sine and cos as well. Notice that if you have 1 over a function, that's the derivative of a natural log. 1 over x is the derivative of a natural log. So if you see 1 over something x, ax plus b, well, you're going to say it's going to be a natural log, but it would have a chain rule, so I'd have to divide by a as well. Same thing with e to the x. If you see you're doing an integral of e to the x, you know that it's going to stay the same, but if it has a simple chain rule, you're going to have to divide by a as well. Especially with natural log, I find that this is the one time that I really use that rule that if you're multiplying by a constant, you can bring that out in front. Just so that I can write this in the form of 1 over something. Because to integrate, to get an answer of natural log, it's the hardest integral to recognize, because it doesn't look anything like natural log to begin with. In fact, it looks more like a power rule than it does a natural log. So I find this is a time that I like to factor out that 15. Then I know that my answer is going to be 15 natural log 3x minus 5. This would have a chain rule, so we're going to also have to divide by 3 plus c. And if you wanted to, you could simplify this. If you're ever curious, did I get it right? Because sometimes integration's harder that way. You can always take the derivative at the end to see. What would happen if I did the derivative of this? If this was y equals, y prime would be 5 times 1 over 3x minus 5, chain rule times by 3. Does that match up with the 15 over 3x minus 5 that we started with? Yes, it does. So now I know I've done this right. I've checked it out. Because what's going to happen is if you're going to make a mistake, it's going to be with the numbers out in front. You might forget to divide by the 3. So then if you did the derivative to check and find out, ooh, it doesn't quite match, maybe that'll trigger your memory to say, hey, maybe I didn't check to see if there was a chain rule involved. So here's an e to the x one. These ones are easier to recognize because nothing's going to change. But if you did the derivative of this, there would be a chain rule where you'd multiply by -3. So integrating, we divide by -3 plus c. Here's sine and cos. Remember that sine and cos with the integration gets confusing because they're so close to the derivative, but now the negative signs are getting mixed up. So again, you have to have some sort of system to help you remember. And again, I'll tell you, remind you my system. I remember the graph of sine. I remember that the tangents right at the beginning are positive, so I know that the derivative of sine is positive cos. So that means integrating cos will give me positive sine. The derivative of cos, if I think about my cos graph, oh, that's a bad cos graph because there we go, maximum there. My tangents start off becoming negative. So it's going to be a sine graph that's a negative sine graph. So that means if the derivative of cos is negative sine, if I'm integrating sine, it would have to go back to negative cos. So here I'm finding the integral of 3 sine 6x minus 7 dx. So since cos goes to negative sine, sine will work backwards to negative cos. And since this would be a chain rule and you'd be multiplying by 6, you'd divide by 6, simplifying this. Would give you negative 1/2 cos 6x minus 7 plus c. My very first year teaching calculus with handout notes, I made the mistake of putting the negative in the wrong place in my notes for the sine and cos. So not only is it hard to remember to begin with because they're so close to each other, it didn't help that the notes were slightly wrong. Well, they were not slightly wrong, they were extremely wrong. And so I had to correct them in the notes, but if you weren't there that day and you had the wrong notes, then it's like, oh. So I have negative cos nightmares. Here's a negative cos nightmare. So the derivative of sine is positive cos. So going back from cos to sine would stay positive. That means if they were both negative to begin with, they'd both stay negative, and work backwards, they'd both be negative to begin with. So now we're working backwards from a negative cos. It will be the same sign. The chain rule would mean we'd need to divide by 9 plus c.